Hi, students. We'll continue today on the subject of Markov processes with stochastic differential equations. So I'll just switch the camera to the board now. So if it's working, yep. Good. So we'll be dealing with Markov processes now that evolve in continuous space and continuous time. And it's a slightly different subject. This is chapter 5 in my notes. So we're skipping in a way chapter 4, but I'll be using some elements of chapter 4. So I'll point this out actually as I go along. So I'll be following the lecture notes that we have on the Dropbox or the lecture notes that we have on my website. So make sure that you download them and then you can follow the material from there. So to begin, I'm just going to go with the introduction to give you an idea of what I want to present today. So the idea builds on a dynamical system. So I think you've seen ordinary differential equations, so ODEs, ordinary differential equations. So I think you're familiar with this. These are equations of the form d dt xt is given by some function of the state, and maybe the function depends on time. And with this, you have to put some kind of initial condition, which I will write like this. So often we model physical system with this sort of equation, a differential equation, and x will represent the state of the system in time, and then you want to represent the evolution of that state as a differential equation. Here I'm writing a first order in time differential equations. It could be second order like Newton's equation, but we know that any second order differential equation can be mapped onto a set of first order equations. Maybe I'll mention this at some point. And it's true also for a higher order differential equation. So this is a deterministic evolution in the sense that if you look at the evolution of the state in time, if you fix the initial condition, then you're going to have a specific deterministic trajectory in time. If you fix the system at the same initial condition, you get only one trajectory. That's the trajectory, that's the solution of the differential equation. And this is deterministic in the sense that there's no randomness here. And this is emphasized by the fact that we're not writing xt as a random variable. It's just a variable. It's a function of time. It's a variable x expressed as a function of time. Okay, so we use this in physics and engineering and chemistry to model many different systems, and again, these are deterministic systems. But often what we're faced with is a kind of differential equation that has some disturbance, some noise included in it, and we want also to model this. And then we'll do this with stochastic differential equations. So what we'll have here now is a kind of differential equation involving a random variable, and this will be also given by some function of the state. Maybe the function depends on time, but we want to put some disturbance, which will be a noise. And for us, this will be an additive perturbation. This will be an additive noise that we add to the stochastic differential equation, that we add to the differential equation. So it's basically the same equation, but we add some noise, and that noise is what I want to discuss first, and then we'll be discussing this kind of stochastic differential equation. So now this is now a random variable that depends on time, so it's a stochastic process. It's given by two terms, a deterministic evolution perturbed by noise, and then we'll spend some time trying to define how we can come up with a noise model, a mathematical noise model. With this, we also have to specify the initial condition, and then we can fix the initial condition to some value, or we can fix the initial condition as a random variable also. So we have actually two sources of randomness. We have the evolution itself, which is perturbed by a noise, and we can also fix the initial condition with some probability. So instead of fixing the value, I could fix the initial distribution for the process. Okay, and then we'll get to see this. Now, the physical picture that I get out of this is that instead of having a specific trajectory now, I have a stochastic process in time. So now I have a random variable that evolves in time. If I fix the initial condition, I can simulate the system and I'll see some kind of random trajectory. And if I redo the simulation, or if I redo an experiment where I can measure the state, from the same initial condition, I can see another trajectory. Okay, so now I have a family of trajectory that will appear with some probability starting from the same initial condition. So now the system is stochastic. I don't have a deterministic trajectory. The initial condition does not specify the trajectory. I have a family of trajectories with given probabilities, and this is now a stochastic process in the same sense that we've seen in discrete time, or yesterday with the discrete state and continuous time. Okay, so now the feature of that process is that I'm evolving in continuous space. In fact, we'll take x now to be a real variable, so I'm evolving on the line, and then time is also continuous, just like yesterday, so it's continuous space, continuous time. Okay, this we will call a stochastic differential equation, but before I get to writing an equation like this, I want to spend some time trying to define what the noise is. Now, there are many models for the noise. You might have heard things like Gaussian white noise, color noise, Levy noise. So there are different ways to actually include noise into a differential equation and different models of noise that will correspond to different physical situations. But the noise model that we'll take for this course is Gaussian white noise. And Gaussian white noise is Gaussian, it's uncorrelated in time, that's why we call it white, and it's based on the notion of Brownian motion or the Wiener motion. So this is what I want to introduce now, and this is part of chapter 4. So I'll define Brownian motion, and then we'll see what the properties of Brownian motion are, and then I'll go back to the stochastic differential equation, and then I will put that Brownian motion as a noise, and then we'll get to study now the properties of the stochastic differential equation. Okay, so at this point, what I'm going to do, which is not so good in terms of teaching, but I need to do this, is to go to chapter 4, and then take some elements from chapter 4 about Brownian motion. So I'm just going to do a quick jump on chapter 4 on Brownian motion, and I have two sections that I want to cover about Brownian motion. The first one is 4.2. It's called the Gaussian random walk. Okay, so the Gaussian random walk is a displacement random variable that is defined as a sum of displacement. So I have n jumps, and so the total distance that I have after these n jumps is denoted by Sn. So Sn is the distance after n jump, it's the displacement. It's a Gaussian random walk because I'm going to take each jump to be a Gaussian distributed with mean mu and variance sigma squared. So this means that each jump is distributed according to a normal distribution with mean mu and variance sigma squared. I can also write this actually as the previous displacement plus the last jump. And this should be natural to you. I have a first jump, this is the first displacement. I have a second jump, so then the displacement I had before plus the new jump gives me the new distance that I have. Okay, so this is a basic random walk, and it's got some properties that we can actually get. This displacement is actually also Gaussian because the sum of Gaussian random variable is Gaussian. And it has a mean. What is the mean of the random walk? The mean of the random walk, you can calculate it, is n times the mean of each of the jump. That's good, that's quite natural. And it also has a variance, the variance of the random walk, because we're dealing with independent, I should have said this here, independent jumps. Independent jumps. So they are ID, identically distributed and independent. This is n times the variance of each of the jump. So it's n times sigma squared. Okay, and in fact, again, as I said, the distribution, the density of the displacement is a Gaussian. So if I know the mean and the variance, I can write it down directly. It's 1 over square root 2 pi n sigma squared, that's the total variance, and I have the exponential of s minus n mu squared over 2n sigma squared. So this is the PDF, this is the probability density of the displacement of the Gaussian random walk. Okay, main points again is that if you sum some Gaussian, this is still Gaussian, so the density is Gaussian. You only need to know the mean and the variance to characterize a Gaussian. The mean is just n times the mean of each of the jump, and the same thing for the variance, so you get the distribution directly. Good. This is the basis of the Brownian motion. Brownian motion is basically a sum of Gaussian displacements. But now it's a sum of Gaussian displacements in time. So that Gaussian random walk, if you want, is a random walk in discrete time. This is the time index after n time steps. What we're going to do now for Brownian motion is that we'll try to put this in continuous time. And this is the next section, 4.3. This is called Wiener motion. And in physics, so in maths it's called Wiener motion. In physics it's called Brownian motion. The way that the Brownian motion is defined is that we want to define this now in continuous time, and then I'll denote the Wiener motion or the Brownian motion by Wt. What we'll do is that we'll do a Gaussian random walk, but we'll do a Gaussian random walk in steps of delta t. So first I'm going to start at 0, and then I'll do a jump here, and this will be the jump that I have here, maybe x1, and then after another unit of delta t, I can do another jump here, x2, and then so on. And then I'm going to have n such jump, and I'm going to end up somewhere here. And that's my Sn. Okay? But I want to make an interpolation of that in terms of, I think there's a microphone open here. Then I want to take the random walk that I built over discrete time and interpolate this in continuous time to build a continuous time process. So this is what I'm gonna do. So I have n is the number of jump, it's the time divided by delta t. And I start the process at 0. We always do this. Okay, so I have the random walk. The random walk is Sn, just like before. It will be a sum from 1 to n of the displacements. But now, this is the special recipe. I need to take the displacement to be 0 mean and variance delta t. And then we'll see why I choose this. Okay? Now, if you have a normal random variable which has 0 mean and variance delta t, this is the same as multiplying square root of delta t with a normal random variable with mean 0 and variance 1. You can check this if you multiply a Gaussian with mean 0 and variance 1 by some constant, then the Gaussian has the variance as a constant squared. So if I multiply by square root delta t, the variance now becomes delta t. This is actually a recipe for building Brownian motion, and then we'll see why I'm doing this in a second. Okay, so Brownian motion is the continuous interpolation of this. The continuous interpolation. So what I'll do is that I take the points of the random walk as the points of the process. So if I want the value of the process at the time t, what I'm doing is I take a random walk and I take delta t to go to 0, which means that n goes to infinity, and I have the random walk here evaluated at t divided by delta t. And this will correspond to the corresponding n for the random walk. So if I want the value, so what I do basically is I have this discrete random walk, and I just take a continuous limit, so I have more and more jumps, more and more more and more jumps in the random walk, and so this will converge to a continuous time process, which is that Brownian motion. Okay, so this is the easiest way of writing Brownian motion. You write it as a discrete random walk and you take a continuous limit. So this is the continuous limit. Continuous time limit. Okay, so what are the properties now of this Brownian motion? It's a random process. It has a mean, it has a variance. I could also find its distribution in time, and I'm going to write this. It's quite simple to write because the Brownian motion is obtained from the Gaussian random walk, and then we know the mean of the random walk, we know the variance of the random walk, we know the distribution. So I can write down the properties. So properties. The mean of the Brownian motion is the limit when delta t goes to 0 and goes to infinity of the random walk evaluated at t over delta t. We know the expectation, the mean of the random walk is 0, so the mean of the Brownian motion is 0. The variance of the Brownian motion, and this is the more interesting now, is the limit when delta t goes to 0, so n goes to infinity, of the variance of st delta t. We know that this is given by, we have the limit still, n times the variance. So it's n times the variance of each of the displacement, but the variance of each of the displacement is delta t. So this is t. And this is the defining feature of Brownian motion. The variance of Brownian motion for the time t is t. So the variance of the Brownian motion grows linearly with t. And this is what defines Brownian motion. And the reason you see why I took the variance of each of the displacement to be delta t is because I want that variance to be t. So I need to multiply n times delta t to get t. So this is the recipe here. If you want the variance of Brownian motion to grow linearly with time, the variance of each jump has to be delta t. Okay, and then the distribution of the motion itself. So the density then is Gaussian. It's a Gaussian density with the variance that grows with time, so it's this. It has no mean, but the variance grows with time, so this is the density of Brownian motion. If you simulate Brownian motion, and this is part of the exercises for the coursework number 4, which is attached to chapter 4, what you'll see is that as you take delta t, which is smaller and smaller and smaller, you'll get very broken trajectories like this. Okay, this will be your time, and this will be realizations or path of the Brownian motion. So trying to do this will be here 2 realization of Brownian motion, and then you can redo this many, many times on the computer to see realizations of Brownian motion, and then you will see, if you simulate many, that the variance grows with time. So you have more probability to reach higher values as time goes on, which you see here too. Okay, so the density with time, for a given time, you're going to have a Gaussian density like this. For a longer time, you're going to get a Gaussian density with a larger variance. So this will be the density of Brownian motion. So as time goes to infinity, the Gaussian just spreads and spreads and spreads up to like very, very shallow, very, very low Gaussian distribution. Here, there's no, it's not ergodic, there's no stationary distribution. Okay, so this is Brownian motion. The reason why Brownian motion is so important is because it's a nice noise model. It's something that you can see in nature. You might know the history of Brownian motion. Robert Brown actually looking with a microscope at some particle of graphene in water, and then seeing that the particle moves, so or not graphene, actually pollen particles, and then moving randomly, and then wondering why the particle is moving randomly. Okay, so this is a mathematical model of that situation, but it's even more important because it's the model of noise that's mostly used in engineering, in physics, and chemistry when you're dealing with adding noise to a differential equation. And that's the Gaussian white noise. Okay, so I'm finished with chapter 4, so I'm going to go back to chapter 5, and now we go into defining that notion of stochastic differential equation. So now I'm going to section 5.4, and it's SDEs.
Hi, Kubo.
Yes?
I have a question here.
Yep.
So after getting that probability density e power minus w square by 2t, so is there any estimate of the minimum number of realization I need to do in order to get the Gaussian probability density?
The minimum number of what, sorry?
Realization for the simulation of that noise term.
This is a sampling problem. This is an interesting question. This is a sampling problem that we'll try to study on Thursday, tomorrow.
Okay.
So, of course, if you simulate only one trajectory and then you look where the trajectory ends up at some time t, you will never get the density. So it's like you want to build a histogram of many trajectories, and then you want to see whether the histogram is close to a Gaussian distribution. So you need many realizations, many samples to get the histogram which will follow this. This is the theoretical distribution of run-in motion if you had an infinite number of realizations. So you can actually experiment with this on a computer following the exercise in coursework 4. So in coursework number 4, for chapter 4, you have a question exactly on generate many trajectories of run-in motion and see that it follows this. Okay.
Okay. Yeah. Thank you.
There's no actually fixed number. I cannot tell. This is just a statistics problem, and there's not a fixed number that will tell you the answer. Okay. So let's go to the stochastic differential equation. So what I want to write, and I'm going to start with this, is again what I've said before. I want to write something like this. So some differential equation, so this will be a kind of differential equation part. I'm not going to write x as a function of t, I'm just going to write this sub t here just to show that it's a process we've been following that notation. And now we have that noise, this is the noise thing. Okay, so I'm not specifying yet what I mean by this, I'm just writing what I wrote initially, which is this is what we want to do. We want to take a differential equation that we know, and then we want to add some noise to it to make it a stochastic differential equation. So the way we're going to make sense of this and the way that we'll introduce this noise is via discretization again. So imagine that you have your process like this over some time, and what we'll do is that we discretize the process in steps of delta t. So we have 1, 2, and I'm going to have n steps here of delta t, and then we're just sampling the process in delta t to get different points. And n again would be t over delta t. Okay, so what does this mean? If I do the discretization, and I think you know this, I take a continuous time differential equation and I get a difference equation. It means that the variation of the process is f xt delta t plus the noise multiplied by delta t. Right? So here I'm just rewriting the differential equation as a difference equation for a small but finite time interval delta t, which is our discretization interval. Okay, and this is where now the noise will come from. This is the usual Euler discretization term that you would have if you're trying to solve a differential equation on a computer. And here what I'm going to do is that I'm going to put now an increment of Brownian motion. Okay, so it means that what I have now here is x t plus delta t minus xt This is the meaning of this variation here, right? This is the term, this is the state that you have, and this is the next state. So the variation is this variation. This is f of xt delta t. And here what I'm going to have now is plus the variation of Brownian motion. So it's the same thing. It's wt at plus delta t minus wt. So that's the variation of Brownian motion. Okay. I could rewrite things a bit, and I'm going to be, maybe I should do on this board here. So I'm going to put the xt on the other side. So what I have is a kind of recursive equation where starting from this state, I get the new state, and the iteration is plus f xt delta t. And now here I'm going to write this in a different way. You see, this is a variation of Brownian motion. But if I take the Brownian motion at time t and I look at the Brownian motion at the later time t plus delta t, what is different here is only one step of the Gaussian random walk. And so this is a Gaussian step with variance delta t. And this guy here is just a Gaussian random number with mean 0 and variance 1. Okay, so let me explain why I do this again. This is a random variable, which is a Gaussian random variable of mean 0 and variance 1. If I multiply by delta t, then I get a Gaussian random variable of mean 0 and variance delta t. This is exactly what I want because I want one step of the Brownian motion. I know the Brownian motion has a variance t, but one step of the Brownian motion has variance delta t, like we've seen before. And so this is the little disturbance that I'm putting to the differential equation. So the endgame that I have is this. Okay, where was I? So that differential equation will be something like this. The way that you have to understand that addition of noise is that you have the usual difference equation, which is the deterministic difference equation, and then you add a small perturbation, which is a Gaussian perturbation. Maybe I should add this. The Gaussian perturbation of variance delta t. When you do this, you're adding Gaussian white noise to your differential equation. This is what it means. In mathematics, what you'll see is a notation like this. The infinitesimal variation of the process is given by some function of the process times the infinitesimal time increment plus dwt. And so this is an infinitesimal increment of the Brownian motion. Now, the reason why you'd see this in mathematics is because I haven't discussed this, but Brownian motion is not differentiable. So if I try to divide by dt on the two sides, I would get something that looks like a differential equation. But I would have to take the time derivative of Brownian motion. But this guy actually mathematically does not exist. Brownian motion is nowhere differentiable, and you can kind of see this in simulation because it's very jagged. So there's no way you can take the derivative anywhere. It's got spiky corners at all scale. So this mathematically doesn't make sense, but you'll see this a lot in physics. It doesn't matter. It's just if you understand what it means, is that this is just Gaussian white noise. Gaussian white noise is the time derivative of Brownian motion. Gaussian white. Mathematically, it's ill-defined, so mathematicians would actually prefer to use this notation, and this makes sense. There's no problem here because you're not taking a time derivative of Brownian motion. You're only saying that the difference, the increment of the process is given by some deterministic push with delta t plus a small perturbation coming from a variation of the Brownian motion. Okay? And this is just a mathematical notation. What it means really is this. So this, which you'll see in physics, this, which you'll see in maths, really ultimately is just this. Starting from the state, the next state in time will be given by this plus a small Gaussian perturbation, which is independent of time. So you have to always get a new Gaussian random variable that you multiply by delta t to get the next state. Okay, so this is done in simulation by fixing delta t to a small number like 0.01 or 0.001 or 0.05, it doesn't really matter. You simulate in discrete time then the process according to this formula, and what you can do is that you can redo the simulation by taking a delta t time which is smaller. You will do the same in molecular dynamics simulation. You'll be solving a differential equations, which you can solve with discretization scheme like Runge-Kutta, Euler scheme. So this scheme here is the Euler scheme. Okay, so maybe I can put this. This is the Euler part of the scheme. It's the Euler discretization of the differential equation. And the only difference that I have now is that I add a Gaussian perturbation at every time step to the Euler scheme. Okay.
Hugo, there's some questions in the chat.
Okay, yeah. You have a look. This is actually a good point to see the questions. Why do we take the variance to be delta t? So the variance to be delta t, again, is because I want the whole variance of Brownian motion to scale like t. So remember, each of the different jumps will have a variance delta t because I want the variance of the Brownian motion to be t. I have n such jumps, so n times delta t gives me t. This is the definition of Brownian motion, and then you might say, okay, but why do we want that property? It's because it's the property that we see experimentally. If you look at the Brownian particle, so if you go back to the experiment of Brown, if you can calculate the variance of that particle, you see that it increases with time. It's the same if you put a drop of dye in water, you're going to see that dye expanding as a cloud of dye. You can measure the expansion of the cloud, and then you see the cloud actually increases in radius with square root of time, which means that the variance overall grows linearly with time. So because this is what we see physically, we have devised a model of diffusion, of stochastic expansion that has that property, and mathematically it's done like that. Each of the jump must have a variance delta t, and so overall the variance of the motion has variance t. How can we take the square root of delta t outside of the z1? Okay, so this is a mathematical result. I'm just going to write this here. If you take a random variable to be 0, 1, so this is a Gaussian, this is what we call a standard normal random variable, and if you define a new random variable to be a times x, and a is a constant, then this new random variable has a mean 0, but it has a variance a squared. Okay, so a little trick, if I want my delta t to have a variance delta t, a good trick numerically is to take a standard normal random variable and multiply by square root dt. Okay, so this is what we'll do numerically. We'll see this tomorrow when we do this numerically. Okay. There was a question about ergodicity. Okay, but this is something else, I think. How can we have an analog to Runge-Kutta scheme for solving an SDE when we cannot Taylor expand the noise term? That's a very good question. We're not going to see this. There's a text. There are textbooks about discretization schemes for stochastic differential equation, and indeed, building discretization schemes for stochastic differential equation is more difficult because you cannot Taylor expand the noise. Okay, we're not going to see this, but it's a nice subject. It's been studied by many people, and so they are higher order discretization schemes. So the Euler scheme is the basic first order scheme. You can build other schemes, discretization schemes for stochastic differential equation, similarly to Runge-Kutta, but they're slightly more complicated than what you'll have for differential equations for ODEs. I can give some references actually on the website, but if you look at stochastic differential equations or numerical stochastic differential equations, then if you search Google, you'll find some references on this. It's quite a rich subject. We'll stick with the Euler scheme. How does construct numerical adaptive solver for SDE? Because the error could change in a random way for discrete time. It's the same thing. So with differential equation, you have different numerical schemes, different discretization schemes, and moreover, you have adaptive schemes for solving differential equations. So if you're solving stiff differential equations, then you have adaptive solvers that will change the delta t in time to make the solution more precise. For stochastic differential equations, you cannot do this because noise is what we call anticipative. So you only throw the noise in the future, so you cannot refine the noise. So you cannot make them adaptive. So that's a limitation if you want to numerically solve stochastic differential equations. So what you do in numerical solutions is that you fix delta t for a small enough t. If you want a smaller delta t, you have to just redo the whole simulation again. Okay, we'll get to actually discuss this tomorrow. So tomorrow, the topic of tomorrow is simulations of stochastic processes. And so we'll try to see how we can simulate jump processes, so the jump processes that we saw yesterday. And then we'll also cover some methods for simulating stochastic differential equations. But you should see it already. This is the numerical recipe for simulating a stochastic differential equation because it's an Euler scheme in which you're adding Gaussian white noise. So all you have to do is access a Gaussian random number generator. So for instance, in MATLAB or in Python, it's rand_n. So that's the normal random number. That gives you a n01 random variable. You just multiply by delta. Add this to the differential to the Euler scheme to get a solution of the stochastic differential equation. Okay. In fact, let me give you the code. I've got the code just in front of me, so let's do this. So what I'll do now is, let me look at the time. Yeah, we're good with time. So I'm going to do some examples now. I'll give you the basic code actually for solving a stochastic differential equation. And
Hugo,
then,
yeah, I think what you said, I think your screen froze for something. Maybe people did not hear it.
Okay.
I think the last thing what you said, I think it was freezing for some time.
Okay. So what I was saying is that what we'll do tomorrow is to do numerical simulations of stochastic processes. So either jump processes or stochastic differential equations. And so, but for stochastic differential equation, you have the recipe right there. It's an Euler scheme in which you're adding a Gaussian random variable. The Gaussian random variable, you can get it in MATLAB or in Python using this function. This will give you a 0,1 Gaussian, you multiply by delta t, and then you have the perturbation. Okay? Okay, so let's go through some examples of this. Let's take the simplest differential equation that we can think of. It's a linear equation, so something like this. X dot t is minus gamma xt. With the following initial condition, maybe some value there. Okay, what I mean by x dot is the ddt, right? So this is d dt. The solution we know is something like this. If you start with x0, then you have this exponential relaxation in time. This is the solution for x. Okay, and the slope of this is minus gamma. I want to add noise to this. So I'm going to add noise by saying the differential equation now is promoted to a random variable. The stochastic differential equation is going to be minus gamma the state plus the noise, which I've written before as that Gaussian white noise. Now again, what's the meaning of this? The meaning of this is that the increment of the process will be minus gamma xt dt. That's the Euler scheme for the differential equation, plus increments of Brownian motion. Okay, so I go from the differential equation to the stochastic differential equation. Okay, and then if you simulate this now, what you'll see is that if starting from the same initial condition, depending on the noise, you can have random trajectories like this. You could also go I up, because there's a probability that you're not following the differential equation. Now, this is a stochastic process. How can you see this on the computer? Let's have a look at the code. So here I'm going to give you a kind of pseudocode for simulation. Let's assume that I want to simulate the process up until time 10. I'm going to use a certain dt, which will be 0.01. In most cases, this is fine enough. N will be the number of time steps that we have. So this is t final divided by dt. And then I'm going to build some vector that will contain all the iterates. So I'm going to have n plus 1 points, because the first point, and here I'm using a Python notation, is some value, say 2.0. Okay, and now I need to build a loop for I in the range of n. I need to have a loop with n time steps to find the new point is the previous point, so that's the difference equation, minus the gamma, which I haven't defined. I should have a gamma here somewhere. Gamma is the value of the parameter, say 1.0, times the current iterate times dt plus square root of dt times random n. Okay, so that's the loop that will fill the vector for the trajectory, and then at the end I can plot this by saying t-span. Here I'm actually mixing Python and MATLAB notation. I think you will understand what I mean here. Yeah, I'm creating a vector of time, and I want to plot now time, the t-span, versus the vector of points that I have. Okay, so this is a simple simulation that will give you one trajectory of the stochastic motion that comes from the linear motion. Okay, so this is again the Euler scheme, and what I'm doing is just adding a random perturbation, which is a Gaussian, multiplied by delta t. You can control the noise power by defining, say, maybe a little sigma here, and then you can multiply by sigma here. So to make the noise smaller or bigger, so you can play with this. Okay, this is nice. If sigma goes to 0, if you take sigma to be 0, then you're really just solving a differential equation that has no Gaussian perturbation. So you can use this program to actually get that curve. And then it's quite interesting to just switch on the sigma a bit to see the random motion around the deterministic curve. And then if you switch sigma bigger, you'll see that it goes in all directions. Okay, and this is now the stochastic differential equation. Okay. Okay, so this is a very simple example. Let's try to find one. Let's go over one now, which is more interesting physically. Let's take the Newton's equation. So here's another example with Newton's equation. Newton's equation, as you know, is I have mass times acceleration, so this is now mass times the second derivative of the state will be some kind of force. But now we want to say we're not dealing with a deterministic system, so the force is just not deterministic, but we want to put some noise as well to the force. So when we do this, you have to see that the force that you put in a deterministic way plus the noise is a kind of total force that includes two contributions: the force that you apply in a deterministic way plus the noise that is being applied externally onto the system. How do we put this in the notations that I've shown before? Well, it's a second order differential equation, so I need to put it into a set of first order equation. And to do this, I think you know the trick. You define first the velocity, you introduce a new variable, which is the velocity, and the first derivative of the velocity is the acceleration. And so this will be the force total over m. And so this will be F plus the noise, and then we'll use the noise to be that Gaussian white noise divided by M. Okay, so this is interesting, and this is really a fundamental point. Whenever you're dealing with Newton's equation, you're adding noise only to the velocity evolution. The position evolution, which is the velocity, is not perturbed by noise. And this is really important. For Newton's equation, you're not perturbing the position. Position derivative is always the velocity. You don't have any added term here. The noise comes in the derivative of the velocity because the noise comes as an additional force influencing the acceleration only. Okay? So let's take an example. What I'm going to do is to look at the noisy pendulum. Noisy pendulum is quite an interesting one. So the noisy pendulum is basically a pendulum that you just kick in time with Gaussian perturbation. So this is an example that's in the notes. Noisy pendulum. Okay, I'm not going to start with the equation of motion, a second order differential equation for the noisy pendulum, for the normal pendulum. I'm just going to write what the equation is in a stochastic way. So I have two states. I have the angle of the pendulum and the angular velocity, which is phi. So I have a pendulum like this, and the angle is like this, and the phi t is the time derivative of the angle. So that's the angular velocity. Using Newton's equation, I would have an equation for the acceleration of the angle, but that's an equation for the first derivative of the angular velocity, just like I said before. So this will be minus omega squared, that's the natural frequency. You have the sine theta t there with the dt plus the Brownian motion. Okay, so this will be the stochastic differential equation describing a normal pendulum motion, even without the linear approximation. And now I'm putting noise into it, and following the discussion that we had before, I put the noise only on the acceleration of the motion, so namely only on the first derivative of the angular velocity. Okay, and then with this, you see, you can follow the code that I've given before for the linear system. The only difference is that you're dealing with two variables instead of one. Instead of having just xt, now I have theta t and phi t. So if I write the program, I need to have two vectors containing the trajectory of theta and the trajectory of the angular velocity. But this is the different scheme. This is the earlier scheme for it. So you have a time stepping for the angular variable, which is just deterministic, has no noise, and the time stepping for the angular velocity has that noise here, which will be square root dt with that Gaussian normal random variable with zero mean and variance 1. Okay? So this is an interesting example to simulate. Have a look. In the coursework number 5, attached to chapter 5, there's a similar example involving what we call the Kapitsa pendulum. The Kapitsa pendulum is the inverted pendulum where you have a stick and then you try to stabilize the stick. And then you can do this by either shaking the basis of the stick, or you can stabilize the stick by putting some noise at the basis. So you can simulate this, and then you can see that you can stabilize the stick by putting some noise, but if the noise is too big, the stick won't be stabilized and then will fall. So this is a question that's in the coursework. I think it's quite interesting. There's a question here: to simulate a simple Brownian motion, is there any numerical scheme that converges faster than the Euler discretization scheme? No, in order to simulate Brownian motion itself, you can only use the Euler scheme that I've showed before, where you're adding just the square root delta t with the normal random variable, because this is how we define Brownian motion. There are other numerical ways, actually, of realizing Brownian motion in a computer. There's some multifractal ways, for instance, to do this, but they're not very useful for us in terms of simulation. And then we'll get to see this also again tomorrow. Could you tell in slight detail on what are the difficulties in numerically solving stochastic differential equations? I would say none. It's very direct, actually, to solve a stochastic differential equation. If you have anything like this, all you do really is take the difference equation, and then it means you have that time-stepping scheme, which is the Euler scheme, where you add f of t dt plus that square root dt with the z. So this is the easiest thing you can do in a computer. You have that iteration scheme in the same way that I wrote before with the loop. So you have one simple loop in which you're constructing each iterate out of the previous one. So the next state is the previous state plus a deterministic push plus a stochastic push. And this is a small stochastic push. You see delta t is very small. So I'm adding a very small perturbation. The smaller the delta t, the smaller the perturbation. But the whole effect of this is to have a variance that grows with time for the Brownian motion. And this is the normal Euler scheme push that you put to the differential equation. So solving stochastic differential equation is very easy. We'll see this tomorrow, and you can start actually working on this if you want on Jupyter or on MATLAB and so on. Good. Okay. Let me go through one last example, and then I'll introduce something that we call the Fokker-Planck equation, which is the analog of the master equation that we saw yesterday. But before I get there, let's see another example. And that example is relevant for machine learning, data science, optimization. It's based on the notion of stochastic gradient or gradient dynamics. So the example is about gradient dynamics. The gradient dynamics is of the form d dt. You have a certain vector in time, and the dynamics is given by minus the gradient of some potential function. Okay, so what you have to imagine is you have some kind of potential in x, that's your u of x, and then you have a particle, and then the motion is always in the direction of the derivative of the potential. And because of the minus sign, it goes down. So it's always going down the derivative, or in a higher dimensional space, it goes down the gradient. So this is like going down in a mountain, following the steepest direction of a mountain. Okay, so this is steepest descent. This is a gradient dynamics. This is used actually in physics to model some systems, but it's used a lot in numerical simulations to find minima of functions. Because if you write down this dynamics and then you start simulating the dynamics, since it goes down, if you have a minima, then it'll get trapped there because the gradient will be 0, and so you stay there. So what's happening there is that as time goes to infinity, this will go to some critical point corresponding to such that u is a minimum. Okay, assuming that you have a minimum. So I'm assuming that I have a potential function that has a minimum, and so if you solve this dynamics, the state and time will go to the minimum. And the reason why it will go to the minimum is because, again, the gradient will be 0 there, so then the dynamic stops. dx will actually be 0. You can get stuck also onto a critical point, you can get stuck onto a maximum, but let's assume that the function has only a single minimum. So not like this, in fact, something like this. Okay, and then with time, you'll go down, and then you'll reach here, and then you stop there. So you can locate the minimum of a function, and this is used really in practice to locate minima of functions. You can do this numerically. You can use a Runge-Kutta scheme. You can use an Euler scheme. Any kind of scheme actually will work in doing this. This is good, but what if the function then has many local minima? So if you have a function like this, if you start here, you're going to end up here. If you start here, you're going to end up here. If you start here, you're going to end up here. So here, you might not be able to find the true minima. So if you have something like this, you might get stuck here. So there's no way, so if you imagine that you have a high dimensional function with many local minima and a global minimum, it's very unlikely that you'll get to the global minima. You'll get stuck in local minima. And this is a problem that we encounter a lot in optimization, machine learning, data science. One solution to this is that you can add noise to it. And so the noise can actually make you escape a local minima and then get you to a global minimum. And if you tune the noise in some way, you might be able to actually reach the global minimum and stay there. And so what you want to do is the SDE version of this. And this is called stochastic gradient descent. So here what you have is a process that mostly in a deterministic way will go down to the gradient, but also has a noise term that you add to it. So this is now a stochastic version of the gradient descent. Okay, so this is gradient descent, this is stochastic gradient descent. Stochastic gradient descent. You have to imagine that you're going down a mountain, but you're not following always the steepest direction. You calculate the steepest direction, and then you just push yourself in some random direction in a Gaussian way. Now, this is a vector, so here you have to add a vector of Brownian motion. I haven't introduced what is a vector of Brownian motion, but it's just a vector with independent Brownian components. Okay. In one-dimensional, then you'll see this. Now, in the coursework, there's an exercise exactly on this. I'm giving you a function which has a local minimum and a global minimum, and the goal is to find the global minimum. The function is simple enough that you can visualize it and then find it by yourself, but if you want to find it using gradient descent, you get stuck in the local minimum. But using stochastic gradient, then you can actually find the global minimum. What you'll see is that you can move randomly here. Sometimes you'll make a jump, you'll move randomly here. You also have some probability to come back, but this is less likely. So most of the time, you actually reach the global minimum. Okay, so here there's some questions. We are using Euler method to integrate, but we know the error in each step in the case is ODT, but here the error in each step is O square root dt. There's a difference between the variance here being dt and the error term, right? So this is also a subject. So the error that we made by discretizing the stochastic differential equation can be studied, and it's something that's been studied. It's not something that I'll be discussing, but you can see also, you can read about this in textbook about discretization schemes for stochastic differential equation. The error that you make for the Euler scheme with the stochastic term is the error that you would have normally in the Euler scheme. By the way, this is called it's not just called the Euler scheme, it's called the Euler-Maruyama scheme. Okay, so with the noise, actually, it was studied by a Japanese called Maruyama. So this is all, most of the time referred as the Euler-Maruyama scheme. But the subject of error actually is quite interesting, and it depends on the discretization scheme that you use. So for the one that will be using this one, the error is of order dt. Okay, and the questions, what are the other noise models other than the Gaussian models? Okay, so you have different noise models. You see here, the noise model is built by putting Gaussian displacements, Gaussian perturbations that are independent in time. So there are two ways that you can change this. Either you change the distribution of the perturbation to something non-Gaussian, or you make the perturbations in time dependent, correlated. If you do this, if you put correlation and you keep the Gaussian nature of the displacement, this is what we call Brownian, this is color noise. So brown noise, pink noise, maybe you've heard this. These are correlated noise in time. They're not independent, so they're slightly more complicated to implement numerically. Then you can still keep the white nature of the noise, meaning that there's no correlation in time, but you change the distribution to Z. So for instance, Z could be a Cauchy distribution or a Levy distribution, and this is called Levy white noise. Okay, so you can go, there are a bazillion number of models that you can go into in terms of noise models, and then you can go into this. There's less information in the literature on these noise models. Some phenomena, actually phenomena like biological phenomenon, will need other types of noise, maybe not Gaussian white noise. Even in physical situations, you might not want to model the noise as a Gaussian white noise, but something else, and people have done this. And so there's quite a big literature on this, but we won't be covering this. Another question, how does stochastic gradient compare with particle swarm optimization? Well, this is a big question. There's no way I can answer this. So there are thousands of methods for finding critical points and minima of functions, swarm optimization being one of them, and then you have also, I don't know, maybe 100 declinations of swarm dynamics. Stochastic gradient is another one. You have something called stochastic annealing. Maybe we'll see this tomorrow or Friday. It's very difficult to actually compare these methods in an absolute sense. Some methods are better for some problems than others. And then people have developed many different methods that they prefer to use in some context or another. But this is a rich subject. It's quite interesting. I teach actually that subject, but here for the people doing machine learning and data science. There's a certain probability that the particle will never reach the global minima if the barrier is too high with the noise, right? Yes. So if you put noise into the stochastic gradient descent, you'll never reach truly the minimum. You will always wander around it. So there will always be a random motion around it, and even, as mentioned, a probability to go back or to move away from it. So the trick, and this is something that is actually described in the problem of the coursework number 5, is that what you should do is that you should control the intensity of the noise in time. And in time, you just try to reduce the noise, but you don't want to reduce it too quick. You don't want to reduce it too slow. And this is what we call annealing. Changing the noise amplitude in time is called annealing. So if you put this, you have a stochastic gradient descent scheme with annealing. And this is good for finding the minimum. How do we know which noise model is good for a problem? Well, this is physics. And this is science. You might be interested by some phenomenon, either in biophysics, biology, and chemistry, and physics, and then you have to look at your system and see first, so this is a modeling question. What kind of model do I want to use to study that system? Is this a discrete state system? Is this a continuous state system? Is the evolution, do I want to describe the evolution in continuous time or in discrete time? What kind of statistics do I see? So you have to have some kind of information about the system in order to build a model. And that really goes at the heart of what we're doing in physics. It's a modeling question. And this relates to something that I've said right from the beginning, which is that I will never see Markov processes as something fundamental in physics. I wouldn't say that nature is fundamentally Markovian. Markov processes are a modeling tool. They're just very useful at modeling various phenomena, but these phenomena can be deterministic right at the bottom, but because we don't have access to all the variables, they look random to us, and so that's why we use these stochastic models to model them. If we can't find the global minima using steepest descent minimization, can we use the Monte Carlo process? Yes. There's something called you can use Metropolis Monte Carlo to find minima of functions. You can use annealing, tempering. These are all variations of the basic Monte Carlo methods to find minimum. You can even imagine actually taking a bunch of points that you put randomly on your function, and then you just select some of them that have the lower value. Then you just repeat this, and then eventually you'll get to the minimum. So there are many random-based methods to find minimum functions. either using random motion, using random selection, using particle swarm dynamics, and so on. This is a very rich subject. Can we discuss the Stratonovich discretization scheme? No, there is. It will take us too much. What I want to do now to finish is to discuss the Fokker-Planck equation. We have about half an hour for doing this. Maybe what I can mention is that what I'm showing here is what we call the Ito discretization. You see, I'm putting a lot of stuff under the rug. I'm not giving you all the details of what's behind a stochastic differential equation. What I've put there implicitly is what we call the Ito discretization. There are other types of discretization, like the Stratonovich discretization, the endpoint discretization, and so on, and they're all different. And this is a rich subject. I actually discussed this in the lecture notes, but I'm not going to discuss this in the time that we have this week. Okay, so the course really is about giving you pointers, sending you in some directions that you might be interested to pursue yourself, either using the lecture notes in more details or using the references that I've given as extra references, the textbook that I've given there. By the way, Sanjib was mentioning this. I put the PDF of the textbooks. It's between us, right? I hope nobody's working for Springer or Cambridge University Press. I'll take the PDF out very soon, so just keep them for yourself. In any case, you know how to find them. We all know where to find books. Are there any analytical results about SDEs? Yes. What I've discussed here is basically trying to solve SDEs in a numerical way, but you can solve SDE analytically directly. I'm not going to touch on this, but just like differential equations, often you can solve a differential equation just on paper without doing any numerical simulations. But in most cases, even for differential equations, ODEs, you cannot solve them on paper, so you need simulation. And it's the same with stochastic differential equations. There are very few stochastic differential equations that you can solve analytically. Good. I think that's about for the questions now. Continue putting questions. I'll just come back to the chat box in a minute. What I want to discuss now, and this is the last topic for today, is what we call the Fokker-Planck equation. We saw yesterday something that we call the master equation. The master equation was the evolution equation for the distribution of the process. We have something similar for a stochastic differential equation, which is called the Fokker-Planck equation. So this is section 5.5, Fokker-Planck equation. Let's go back to the stochastic differential equation that we have. So we have an SDE, which I'm writing in general as in the mathematical form as a differential equation. So the variation of the process is given by some function plus the noise, which I'm going to write here now with the noise amplitude sigma. So I can tune the noise amplitude of the Wiener motion with sigma. If I set sigma equals to 0, that's just a differential equation. Otherwise, I'm putting some noise. And then moreover, to this, I have some initial equation, some initial condition, which I'm going to fix there. Okay, I'm not going to put vectors here, but let's assume that xt is a vector in Rn, which means that f is a function of Rn to Rn. And Wt is also a vector of run in motion, which I'm going to take here to be Rn2. Okay, so I'm not putting the vector notation everywhere, but these are all vectors. Okay, this is a random variable. This is the state of the system at the time t. So I can write something like the PDF. So the PDF of that process would be Pxt. This will be the PDF, the probability density for the process to take the value x. Okay, so we had something similar yesterday. For the process, I could write what is the probability to reach a certain state at a certain time, and so we have this here. Now, because we're dealing with a real process, a real random variable, this is now a PDF. It's a probability density function. So the density to be at x at time t, this is what it means. That's the probability density for the random variable at time t to take the value x. This depends on the space and on the time. There has to be an evolution equation for this. What is this evolution equation? Well, the evolution equation is the Fokker-Planck equation. So the evolution equation is the following. It's a partial differential equation. ddt of the density is given by two terms. First is the divergence of f p xt. And then there's another term which is 1/2 the divergence. Here I'm going to simplify things a bit. Sigma is just a real parameter. Okay, so then I'm going to have here sigma squared, and here I have the Laplacian px. Okay, and I could write the Laplacian in another form if you want. This is the same as the Laplacian, so this is the same. Okay, so that's the Fokker-Planck equation, FP equation. In components, what this means is the following: ddt, so the partial derivative in time of that function, is minus the sum over the different components of dxi fi x p of xt plus 1/2 of the sum here over I of the second derivative dxi of px. Okay, I'm simplifying. This is not the most general Fokker-Planck equation that you can imagine. Sigma can be a matrix in general, and then you have a more general Fokker-Planck equation. Here I'm just simplifying to the case where sigma is a real parameter. So that sigma here is a real parameter, so we have to put it here. So you have the sigma. This is a pretty complicated partial differential equation. You have a look at it. It's a conservation equation. It's a bit like an equation of fluid dynamics. It basically says that the variation of the probability comes from two terms. This is the transport term that comes from the deterministic part of the evolution, and this is what we call the diffusive term, which comes from the random motion. So actually, this is important. So this is what we call the transport, or the advective term. If you don't have any noise, this is the only term that you have, and this is what we call the Liouville equation. If you have noise, you have another term here, which is what we call the diffusion equation. The diffusion part of the equation. Okay, then you see it's multiplied by sigma squared, so the more noise you have, then the more important this is, and diffusion always comes with the Laplacian. So for instance, if you look at a drop of water that you put into water, then this is pure diffusion. You know the equation in terms of diffusion, it's the Laplacian. The reason why we have the Laplacian is because if you look at the microscopic of the motion, you have all these particles doing Brownian motion. And so what you see at the macroscopic limit is the diffusion. Okay? But this is, again, the evolution equation for pxt. So with this, in some cases, you can solve the equation to get pxt. Okay, this is what you want. But the one thing I'll notice is that if you look at this, it's a linear equation. And this is now ties in with what I discussed right from the beginning. All evolution equations and for Markov processes are linear for the density or for the probability. Okay, so this is a kind of Schrödinger equation for the real PDF of the process. It's different from Schrödinger equation because it's got a term related to the transport and a term related to diffusion. But if you have a look at what's being applied onto P, these are linear differential operators. So I can put them I can write them just abstractly as this big operator acting on P of xt, and so this is a linear equation. Okay? So G would be just this operator plus this Laplacian operator. So again, we get back to this idea that we're dealing with the linear theory. So going back to what we had before then, I could write just formally, just abstractly, Pxt is the initial distribution at time 0 times the exponential of gt. But now yesterday what we had is that G was a matrix. In the master equation, G was the matrix of transition rates. Now G is a differential operator. So what's the meaning of this? This is very abstract. There's no way you can make sense of this just in a very concrete way. It's just a formal notation to say that this is the solution of the linear equation. Okay? You have the same in quantum mechanics. If I want to stress now the analogy with quantum mechanics, you have an equation for phi. So the partial derivative in time of phi is some operator applied to phi. That operator in quantum mechanics is the Hamiltonian. For us now, it's not the Hamiltonian. It's that operator G that we call the generator. And the generator is this massive differential operator, which resembles in a way the Schrödinger operator because we have that Laplacian, but there's something else here, which is a first derivative. So this is first order, it's a gradient. And G, maybe that's another difference. The G dual is not the G because of that term. The Hermitian of this is not this, it's minus this. The Laplacian is Hermitian, but this is not Hermitian. So we're dealing with linear system, a linear equation, but it's not Hermitian. Okay. I'll finish with then, I'm just going to talk about this equation a bit more, but I want to discuss then ergodic system. I will always finish with ergodic system. We have an evolution equation, and the question is, can we solve it? In many cases, that's the first question you want to answer, and the answer is sometimes. In some cases, you can solve it, but it's very difficult to solve. But there's an easy case, which is for, not an easy case, but an easier case, which is ergodic SDEs. Ergodic SDEs. So just like we had for Markov chains in discrete time or jump processes in continuous time, you can imagine that the time-dependent distribution will go to some stationary distribution in time, and this will be an ergodic process. So an ergodic process will be a process such that if you take the long time limit of this, then you get a stationary distribution starting from any initial distribution. If you have this property, if you're dealing with an ergodic system, we could give conditions for a system to be ergodic, but we're not going to do this because it takes too much time. The P star there will be such that it doesn't involve in time, so the P star will be such that you have this. So this is very similar to the case of jump processes that we had before. An ergodic system will have a time-dependent distribution that goes in the long time limit towards a stationary distribution, which is unique. And that stationary distribution satisfies the time-independent master equation or the time-independent Fokker-Planck equation. So it means that if you apply G to P star, you get 0. So it's an eigenvector of the linear operator with eigenvalue 0. Okay? Again, for jump processes, that operator was a matrix. Here, that operator is a differential operator. So you need to solve a differential equation to get the stationary distribution. And I'll finish by giving you only one example of such an ergodic process that has that stationary distribution, which is the gradient system. So if you start, here's an example. If you start with dxt, which is equal to the gradient minus the gradient of some potential, plus dwt, then you can check from the Fokker-Planck equation that the p star for this is the exponential of minus 2 the potential, divided by some constant, which is the normalization constant. So that's just the normalization. Okay. I'm not proving this because this is part of the coursework. So coursework number 5, you have to prove this in some of the questions there. So this is one case where for some potential, so if U is confining enough, not all U actually will have a stationary distribution, but if the U, the potential is confining enough, then you have a stationary distribution, so it's ergodic. It's a unique stationary distribution, so it's ergodic, and this is the stationary distribution. And then you can check this by plugging this distribution into the Fokker-Planck equation, and then you'll see that it satisfies this equation. Okay. This is the simplest system. And this is also called an equilibrium distribution. This is also called a Gibbs distribution because it describes an equilibrium system that satisfies detailed balance. Okay. I haven't mentioned or haven't defined what detailed balance is, but if you know, then it's related to this. So this equation, this process satisfies detailed balance. Okay, I think I'll stop here. We're at 11:53. I can take some questions. There's one here. How do we define uniqueness of P star in this case? So this is an interesting question. It's a big question, but we have the same questions for Markov processes and then for John processes. For a given process, how do we know if we have a stationary distribution? We can have no stationary distribution, we can have one, or we can have many. And the same can happen here. If you start with the Fokker-Planck equation and you try to solve it, this is a PDE, it's a partial differential equation. And then you have to see if it has a solution at all, if it has a time-independent solution. Maybe it has an infinite number of stationary solutions. But ergodic processes are interesting because they will have a unique one, and it will be reached from any initial distribution for the process. It's not so easy to, from the look of a stochastic differential equation, to determine whether it's ergodic or not. But again, all the examples that I give in the lecture notes, or many of the examples that you'll see in the textbooks that I gave as references, most of the processes there are actually ergodic. You can also check in simulation whether a process is ergodic or not. So uniqueness of the P star will be to say that there's a unique solution. The Fokker-Planck equation has a unique solution. And maybe you can prove this mathematically, maybe you can check it numerically to some extent. It's a difficult question actually to check uniqueness of that PD. Okay. Other questions?
Yeah, hi. I'm trying to make sense of these various discretization schemes and adaptive procedures, like some questions came up. So when we say that a stochastic differential equation is specified, what do we mean? Do we mean that like there is some discretization which is already set up and that's what specifies the dynamics? Or, I mean, is there like some differential equation we write down, then we worry about how to discretize it? Or what is the typical situation we think?
Okay, so this is something I haven't mentioned because it goes too deeply in the technical things, but when you write a stochastic differential equation is defined by me writing something like this. And maybe actually the noise can depend on the space, and then you have the noise here. If I write this, actually, I'm implying that there is a discretization. Okay? And if I change the discretization, I need to actually specify it. So the one thing I haven't mentioned is that for us, all the equations are discretized in the Ito sense, which means that the point I put here is always the point before. So if I discretize my point here, it will be xt plus, and now here I take xt. I don't take the mean of xt or xt plus delta t, or I don't take the final point. I put the left point. So this is the kind of left point Riemann integration scheme for the stochastic differential equation. And if I do the same here, then this is the E2. If I do this, then this is the E2 discretization. So a stochastic differential equation always has to come with a discretization by you saying, I'm going to use this discretization. You're not bound to use that discretization. Someone else could actually decide to say, oh, I'm going to use a different discretization. I'm going to use maybe this. I'm going to keep this one here. But this one, I'm going to use the middle point. So I'm going to use t plus dt plus xt divided by 2. And then here I put a delta tz. If you do this, this is another discretization that's called the Stratanovich discretization, which gives you a different solution from the E2 discretization. So the one thing I haven't mentioned is that when you write a stochastic differential equation, you have to say which discretization you're going to use. See, for differential equations, you never have to do this because differential equations will be invariant with the choice of calculus or discretizations that you use. If you use a Riemann left point or a midpoint or a right point, if the system is smooth enough, you know from calculus that it doesn't matter whether you integrate with the midpoint rule or the left point rule or the right point rule. But for stochastic differential equations, it does matter what kind of discretization you choose. So again, this is the E2 discretization. That's the one I've been discussing, and this is how you write it. If you want to use a Stratanovich discretization, what people do is that they put a round dot here to say, I'm going to study this stochastic differential equation, but the interpretation of the discretization I use is the Stratanovich one. What we've done is E2. Okay? So this is a very rich subject. It's something that's covered in textbooks on stochastic differential equation. It relates to what is called stochastic calculus. Okay, so you can build a calculus of stochastic functions, stochastic processes, but now the left point rule, the midpoint rule, the right point rules that you would consider in calculus as being the same in normal calculus, they actually lead to different results in stochastic calculus. Okay, that's quite an interesting subject. It's covered a bit in my lecture notes, but I'm giving more references in the lecture notes on this. We don't really have.
Thanks. So one more question. So is there, in some sense, like the stochastic differential equations, there's some sense we can think of them as like stiffness kind of characteristics. Are there anything like that for stochastic equations, just like how we have for ODEs, stiffness issues? Is there anything like that?
Yeah, all the numerical problems that you can have for differential equations, you might have them also for stochastic differential equations. So if you have a stiff, I'm doing this a lot actually. In some cases, I'm dealing with very stiff systems. So the delta t that I have to choose has to be super small. So this is always a numerical issue. So anything that relates to the stability of the integration that you might actually face for differential equations, you might see them also for stochastic differential equations. There's lots of numerical issues that you might be facing. And then for us, the only solution that we have is to decrease that delta t. You cannot do it times step. You can do a bit of running if you want, but you cannot do it that times step.
Okay, thank you very much.
Good. Okay, have a look at the coursework. Feel free again to send me questions by email if you want. I had a few questions yesterday. That's nice. So I'm available if you have any questions. As always, you have the solutions for the coursework, and then you have the Python code also for the simulations. My favorite subject actually is stochastic differential equations. I like jump processes, but this is, in a way, for me, that feels more physically because I can simulate this. It relates to dynamical system. This is what I've been doing also for quite a long time. So I love stochastic differential equations. Good.
Sir, at the end, you were making some comment about detailed balance. Can you repeat that? I missed it.
Yeah, I'll try to cover detailed balance on Friday. Okay, the only thing I'm going to say is that the stochastic gradient, the stochastic differential equation that is based on the gradient, has a stationary distribution, which is the distribution that I've shown before with the exponential. And the stochastic differential equation, the process defined by that stochastic differential equation satisfies detailed balance. Okay, and this is related to there's a notion of current for Fokker-Planck equation that I haven't discussed, but the current is equal to 0 here. The process is reversible, and then so on. So this is it's an interesting topic, but it's a very rich topic. It goes beyond a bit what I've this chapter. But I'll try to give a few elements on Friday if we have time.
Okay.
Excuse me. Hello. Like regarding the uniqueness of this P star of X, like in Markov processes, we have conditions like detail balance, irreducibility, and aperiodicity, because there we were dealing with matrices, so it was easier to formulate those conditions. But do we have similar things here? Because we are dealing with differential operators here, not matrices.
So it's exactly right. For Markov processes, for Markov chains, discrete state Markov chains, you can say that if the Markov matrix is irreducible, aperiodic, then you have an ergodic Markov chain. Here for the continuous state process, I have no such result. So it's all about looking at the Fokker-Planck equation as a PDE and then trying to find conditions for that PDE to have a unique non-trivial solution. So this is really like a PDE problem. It's quite difficult. So the difficulty here is much higher than for Markov chains or even jump processes.
So the problem just goes to the calculus.
Yeah, it goes to calculus now. In the subject of PDEs, solutions of PDEs. Yeah.
Okay. Thanks.
You have the same problem when you're dealing with quantum mechanics, but it's just never mentioned. If you start with the time-dependent Schrödinger equation, how do we know that it has a solution? Even the time-independent Schrödinger equation, there's an issue about existence of solution there, but that's never mentioned because all the examples that you'll see in physics textbooks actually lead to unique solution for the wave function.
Hello. I sent you some doubts yesterday through email, and regarding one of the solutions of this birth-death processes, where you said that we can just guess a solution while looking at this difference equation. So I kind of find it hard to actually guess it. So is there any way, would you like to point out how to derive the solution analytically? Because I could put the solution back and realize that, okay, we can obtain the solution in this way, but a priori guessing form of the solution is kind of hard.
Yeah, but this is really a mathematical question. So the master equation in this case actually was a differential equation. So this relates to how do you solve difference equations in general, and this is quite different. In this case, it's just easier because I know the process a bit. Maybe you can simulate the process a bit and then guess what the stationary distribution looks like. Here, actually, the crux of the solution is to realize that you have a geometric process. So the distribution has to be geometric with the state. In general, it's very difficult, even with difference equations or differential equation, to solve them. So this is really mathematics. In many cases, we cannot solve analytically something. But this is a game that we play a lot in physics. We can sort of guess a solution of reverse engineer a solution and just check that it is. And I thought that was just an easier way to present that problem to students and the solutions of that problem. I'm sorry, I don't have like a complete answer for this. I can't think. I don't know what the general method of solution is in that case. I just know that this is the solution.
All right. I'll look for it. Okay.
Yep.
Thanks.
See you tomorrow.
Yeah. You have a good day. See you tomorrow.